Hello, everyone. Welcome to the Joseph Priestley Society lecture series. My name is Miranda Bennett, and I am a philanthropy manager at the Science History Institute. The Joseph Priestley Society, which is also known as JPS, is a volunteer-supported program that promotes a deeper understanding of science, technology, and industry, with an emphasis on innovation and entrepreneurship. Today's program is focused on the history, present, and potential for geothermal energy. Before our panelists begin, I want to bring your attention to the collections and programs of the Science History Institute. There are many resources from the Institute that reveal the history of geothermal energy as an alternative power source. For example, in our oral history collection, you could hear about the installation of a geothermal system in Ambler, Pennsylvania in the 2010s. And we have a film exploring the role that geothermal wells played in the conflict over Proposition 65 in the 1980s. And in our digitized Distillations magazine, you can read about the connection between geothermal heat and Joseph Priestley's apparatus for making artificial mineral water. So I encourage you to search our digital collections and our website, where you'll find many other stories behind the promise and complexities of geothermal energy. Our moderator for today's program is Bill Tazinski, who is a partner of the Unami Group, offering sales support and consulting in specialty chemicals and lubricants. Prior to that, he was a co-owner of Ivanhoe Industries, a specialty distributor, and he has extensive experience in market and product development. Bill holds a PhD in organic chemistry from Cornell University and a BS in biochemistry from Manhattan College. He's a longtime member of the Joseph Priestley Society Executive Committee. Bill, welcome, and thank you for moderating.
Thank you, Miranda. It's a nice way of saying I'm old. So first, I want to thank everyone who signed up and glad to have you with us, and especially thank our panelists, Brian Schmidt, Jill Karpinski, and Andy Feick. Brian is a historian at Geothermal Rising. He'll provide us with an overview of the geothermal industry, its history, and how the technology has evolved over the years for use in geologically active areas as well as other areas. And Jill and Andy will speak about their experience, their project at Swarthmore College to convert the campus heating and cooling system to geo-exchange as a climate mitigation strategy, and how it's being implemented economically while minimizing disruption to campus life. And with that, I will turn it over to Brian and remind you that when you have questions, put them in the Q&A box, not the chat. We'll be monitoring that, and we'll get to as many of your questions as we can at the end of the session. So, Brian, it's all yours.
Thank you, Bill. Lovely introduction, and I'm happy to be here and excited to talk with everyone about geothermal energy. As Bill mentioned, I am with Geothermal Rising. Let me just go through the quick outline of what I hope to talk about here today. I'll give you a little introduction to the organization that I'm with, and then an introduction to geothermal energy, talk about the history and the applications of it, and then some of the more recent technology and innovations that are going on, and hopefully address a few misconceptions and challenges, and then talk a little bit about what's next. So who is Geothermal Rising? We're the largest and oldest geothermal membership organization in the world. We were founded in 1972. We are a 501c3 nonprofit dedicated to promoting geothermal energy and supporting those who develop and use it. We work to build and empower the geothermal community through education, networking, and advocacy. And we actively educate and engage in policy at the federal, state, and tribal levels in North America. So what is geothermal energy? Simply put, it is the Earth's natural heat. We can harness this heat for producing electricity or for heating, cooling, and a number of other applications. It's reliable and renewable. It provides consistent energy day and night. It isn't dependent upon weather patterns or anything like that. It's always there. And as I mentioned a moment ago, it's very versatile in its applications. It can be used for heating and cooling of homes and commercial buildings. It's used in a number of industrial processes and power plants. And it is a sustainable solution that helps reduce carbon emissions and the dependence on fossil fuels. How is this heat generated, and how does it reach the surface? As most of you probably know, heat is generated deep inside the Earth from both the core and the mantle. It moves upward through various layers of rock, traveling by both conduction, which is through the rock itself, or by convection, which would be through fluids. In some places, this heat gets trapped close to the surface, and these are the areas that are most likely to be used and exploited for the geothermal energy involved. We can access these areas by drilling deep wells to capture the heat for energy use. And just to give little bit of a timeline here, we've been using geothermal energy in one way or another since before recorded history. Ancient hot springs were used by cultures all across the world for a variety of reasons. However, in terms of actually using this for what we would call the current applications, that all started in the late 19th century in Italy. Larderello, Italy. In the late 19th century, there was a number of experiments going on there looking into geothermal technology. And then in 1904, Prince Piero Conti in Larderello produced the first geothermal electricity. And I believe it was 7 years later in 1911 that the first commercial plant went into operation there. And Italy was the only country producing geothermal energy up until I believe 1958, when New Zealand and followed shortly thereafter by US, Iceland, Japan, a number of other countries jumping into it in the latter half of the 20th century. And today, it helps power homes, cities, and industries all across the world. This is just a little fun map of the world showing some of the early uses of geothermal resources. The hot springs in North America were sacred places of healing and peace. The Roman Empire had vast bathhouses scattered all throughout the empire there. Italy had spa towns as early as the 1300s. Japan had hot springs for healing and luxury. In Philippines and Indonesia, the geothermal sites were linked to gods and various creation stories. And in the Andes and South America, the volcanic soils were heavily involved in daily life and rituals. As far as modern applications, it's split between sort of three different temperature ranges. Low temperature, which is up to 122 degrees Fahrenheit, mid temperature, which is up between 122 and 302 Fahrenheit, and then high temperature, which is above 302 degrees Fahrenheit. And depending on the heat involved, you have different applications available to you. So with the low temperature, some of the direct use applications include agricultural applications, which can include crop drying, milk pasteurization, and heating greenhouses. Aquaculture, there's a number of tilapia fish farms that use geothermal waters in their fish farm. It's still used for balneology today. There's a lot of the tourist industry involved in that. We have heating and cooling of either individual buildings or in a district-wide setting, which I believe Andy and Jill are going to talk a bit about that a little later. There are industrial applications such as food processing, heat bleaching, and process heat, or for snow melting. And what defines all of these as direct use is that in all of these cases, you're taking the actual fluids and using those to provide the heat. You're not converting it to electricity or anything like that. You're just using the fluids themselves. So looking at some of the heating and cooling options here, on the left, you can see sort of an individual house geothermal heat pump system. And the way this works is it takes advantage of the fact that the temperature below the surface of the planet remains a very surprisingly steady, constant temperature. And so in the summertime, when it's hot, you take your circulating fluids through there and bringing the cooler fluids up into the building to cool it. And in the winter, when it's cold, you're circulating them through there and warming them and using those warm fluids to warm the house. On the right You can see the district heating and cooling system, much more involved system, but really works on that same principle of in the summertime, we are pulling cool water up, and in the wintertime, we are pulling hot water up and using that to heat or cool the buildings involved. In the case of the district heating, you'll have an energy station that's managing all of this, and it's, as I mentioned, a much more involved process, but it's basically doing the same thing. So then if we look at high temperature options, these are generally different means of producing electricity. And so there are thermal energy storage is a bit of an exception, and that's more a means of harnessing it, and but it's generally also used in electricity production. So you have hydrothermal systems, which is the traditional ones. I'll go through these in a moment with a different slide. Engineered geothermal systems, also sometimes called enhanced geothermal systems or EGS. And advanced geothermal systems, also called AGS or closed loop systems. And here we have a slide showing each of these things. On the far left is the traditional hydrothermal system. All of the earliest geothermal power plants worked on a system like this, and they work on it. It's also known as a dry steam system, and they require an aquifer that has three things. You need enough heat, you need enough fluids, and you need enough permeability in there for the fluids to be accessible. And if you have all of those things, what you do is you just pull all of you pull the steam up and use that to power a turbine, and then once the fluids have cooled, you inject them back into the reservoir so they can heat up again. In an advanced geothermal system or an AGS closed loop system, you don't need to have a reservoir. The entire thing is a closed loop, and you have a working fluid inside this loop of piping that is usually something that vaporizes at a lower temperature than water. And you circulate it through there, and so you're not actually pulling any fluids from the ground. In an enhanced geothermal system or EGS, it works very similarly to the hydrothermal system, but it's for places where you have enough heat and you have enough fluids, but you don't have the permeability. And what you do in that case is you drill in and you create a fracture network in there through hydrosharing or hydrofracking. And it basically becomes a man-made reservoir at that point. And then at that point, you're utilizing it the same way you would a traditional hydrothermal system. The one on the far right, the super hot rock system there, is still very much, I would say, in the experimental developmental stage. There are a few very promising projects out there, and it's looking really good. What this involves is drilling much deeper down and getting into supercritical fluids at upward of 374 degrees Celsius. As you can imagine, the challenge involved there is equipment design and having your equipment that can survive the kind of heat and pressure that would be taking place at those depths. But there's been a lot of advancements recently in that equipment design, and things are looking promising. So if we just look at the traditional hydrothermal high temperature electricity generation, this map here is a heat map of the United States, or the continental United States at least. And you can see the little white dots are power plants. And you can see they're all in the hottest areas there, and they're all also, what you can't see, also places where we have a good aquifer with permeability and fluids there. There is currently about 4 gigawatts of geothermal production in the country. If we're just talking about identified hydrothermal resources, there's another 9 gigawatts that have been identified and could be used. And it's estimated that there's another 30 gigawatts of undiscovered hydrothermal resources around the country. But this is still mostly going to be restricted to the Western United States because of the geology involved. That as you look to the whole eastern half, you don't see any of the same hot spots near the surface. So we're still, as far as traditional hydrothermal, somewhat geographically restricted. And to talk about that a little bit more, there are really 3 different types of hydrothermal power plants. The one in the upper right is the earliest version there, that's the dry steam power plant. And this is very much needs very specific requirements. And that's why you initially in the 20th century, we're only seeing geothermal power plants pop up in very specific geographic locations, because you need not only do you need the heat and the fluids and the permeability, but you need it all with dry steam coming up in your well. However, you have that situation, it's great. You just pull that dry steam up, use it to power a turbine, and then re-inject the cooled fluids back into the reservoir so they can be heated up again. On the lower left, you see a flash steam power plant, which flash steam plants are for aquifers of hot pressurized water. And what happens is that as the water moves upward, it loses some of that pressure, and some of it converts to steam. The steam is then separated from the water and used to power a turbine, and then eventually cooled and re-injected back into the reservoir. In the lower right is a binary cycle power plant. And in a binary cycle power plant, you don't actually use the fluids directly. You have two separate loops. You have the loop that you're pulling up the hot fluids from under the ground and re-injecting them. But then parallel to that at the surface, you have another loop of a working fluid that vaporizes significantly lower temperature than water. And then so the fluids from underground are never actually touching the turbine. Instead, it's that working fluid that is going to vaporize and flash and power the turbine. Binary cycle plants are nice for a couple of reasons. One of which is that because of that lower vaporizing point, it can be much more efficient, and you can operate with a lower temperature resource to begin with. And the other is, since it's a totally closed system, that there is little to no emissions from binary power plants. EGS, as I mentioned, works very similarly to a traditional hydrothermal system, except that you don't have the permeability inherent in your system, and you need to create it by basically creating a man-made reservoir. This map shows a few of the primary EGS projects in the country right now. Further's Project Red in Nevada has recently had a couple of really nice breakthroughs there. And then you have the Cape Station and the Forge project. Forge is the Frontier Observatory for Research in Geothermal Energy. It's a Department of Energy funded field laboratory specifically researching EGS project. And then you have Sage Geosystems down in Texas working on a EGS geopressure system that has also shown some really, really good results. There is the potential in the Western United States for 520,000 megawatts just for using EGS. Because of the need for that heat with EGS, it would still primarily be in the Western US that EGS would be used. But that means a total potential capacity of somewhere around 35,000 gigawatts. This is just a little for AGS and the advanced geothermal systems, the closed loop, just a little diagram showing how that works. As you can see from the on the left there, the close-up section, the cooler fluids are pushed down into the system, and then as they warm, they come up on the outer piping of the system there. And as far as AGS goes, similar map, same heat map. And here's some of the projects that with AGS, Greenfire Energy has a couple of projects going on. One is at the geysers in Northern California, and one is at the COSO Naval Base in Southern California. And both of these are working with existing hydrothermal systems and working to make them more efficient. And so they're installing a closed loop aspect into an existing system, and again, with really, really positive results. We have XGS Energy is working on a project in New Mexico, and Exceed Geoenergy has a couple of AGS projects in Texas. There's also a very promising project in Germany right now by Ever Technologies that is has gone online recently with I forget the number of megawatts, but it's very promising to see. So what does this mean for the market? Projections say that just looking at next-gen geothermal power, which is AGS, EGS, and potentially super hot, we could be looking at, by 2050, a installed capacity of somewhere around 800 gigawatts. And if you look at that, largely a lot of that would be coming from China and the United States, but there would also be significant development in India, Southeast Asia, and Europe as well. So let's look at a couple of myths around geothermal. Geothermal energy has had a lot of misunderstandings over the years. And so myth number one, geothermal will run out. And this isn't true. The Earth's heat is not going anywhere, not on our timeline anyway. An individual well might lose pressure, but it's not going to lose heat. The only thing that might run out is fluids, and we can always add fluids. Myth number two, geothermal harms frontline communities. The truth is that Department of Energy has very specific standards on how developers collaborate with local communities to ensure health, safety, and shared benefits. And this is something that I've seen really just in my time within the industry really improve over the years, that they are very proactive these days in reaching out to the communities, making sure that they have buy-in from everyone who's going to be impacted by the project. And it's really good to see. And myth number three, power plants did not mean to do that yet. Power plants take up too much land. One of the beauties of geothermal is that it has the smallest land footprint of any power source. You don't need acres and acres of solar panels or wind farms or anything like that. You just need a power station and some pipes. Geothermal causes air pollution. It is actually a low emission resource. There's no burning of fossil fuels and very minimal greenhouse gas release. And myth number five, it only works in certain places. This was true once upon a time, I think. But these days there is especially with the AGS and with some of the district heating projects, geothermal is definitely available nationwide in some manner. I wanted to mention a couple of upcoming events that we have that we're going to be putting on Geothermal Rising. We have our Thermal Energy Network Symposium in March in Baltimore, and that's going to be focused specifically on these district heating energy networks. And then we have our big annual conference in September in Houston, the Geothermal Rising Conference. And I encourage everyone who's interested to attend one or both of those. And I'd like to thank you. I am happy to answer questions at the end of this, but you can also feel free to reach out to me. My email's on there. I'm just brian@geothermal.org, and it's been great talking to you.
Thanks a lot, Brian. We're glad to have that. Was a good introduction to the topic. And we're not in it's not in a active geologic area. Swarthmore College is taking advantage of a geo-exchange program, and it's an application that Brian covered. And we'll let Jill and Andy speak to that and talk about what they're doing just in our neighborhood to make geothermal and geo-exchange a reality. Take it away.
All right, Bill, thanks so much. And Brian, thanks for that geothermal overview. And now Jill and I are going to provide a synopsis of Swarthmore College's project, which we call 20 by 35, which means we're trying to get to zero carbon on our campus by 2035. And our reference to geo-exchange here, and not just geothermal, is because we are using a system that we take thermal energy from cooling our buildings in the summer, deposit it in the ground, and then we extract it in the winter in order to heat our campus. So we're going to talk briefly about the what, why, and how of this project. I'm going to be the opener and closer in the middle. Jill's going to talk specifically about the technical aspects of what it is that we're doing here for our geo-exchange project. And Swarthmore College is located, we're in the Mid-Atlantic, we're right outside of Philadelphia. I made this little graphic when I was feeling more optimistic about our chances of repeating the Super Bowl, and I haven't removed the Eagles logo there, but it gives you an idea about where we are. And this is important because in the Mid-Atlantic, we're heating a lot in the winter and cooling a lot in the summer. And when we did our study of our campus, we found out that our thermal energy demand is fairly well balanced for what we need for heating in the winter and cooling in the summer, which makes us a good candidate for geo-exchange. And here's the what. So our geo-exchange project 20 by 35 is a carbon-free district energy heating and cooling system for our campus, powered by renewable electricity, and it replaces our legacy steam combustion infrastructure for our campus. We have this nifty logo that we developed. We don't brand all of our projects, but because we're a college campus and this is a 15-year effort that's touching literally every interior corner and much of the physical exterior campus as this work goes on, we felt it was important to talk about the elements in this logo in a consistent way through many generations of students that will come through here, with the sun powering it. The shovel denotes the wells and the digging that's required to install this district energy system. The arrows with the interaction with the ground with thermal energy, and finally the tree representing the sustainability aspects of our project. So, here's how it works in the major components, just briefly with this infographic. We're powering it by renewable energy, even though we're taking energy from the grid to power our geo-exchange plant as we move down through this graphic. Into our geo-exchange plant, we've got heat recovery chillers in the central plant that provide our low temperature hot water and chilled water to the campus. And that water, thermal energy during the summertime comes from our campus buildings. And so as we're cooling, instead of what we've been doing in the past, where we take the heat extracted from buildings and exhaust it to the atmosphere through evaporative cooling, we're taking it now back to the plant, and the heat recovery chillers push it into the well field. So we're depositing thermal energy in the well field all summer long and using the earth like a large thermal battery. And then that stored thermal energy in the wintertime, the heat recovery chillers are extracting that thermal energy from the well field and using it to provide low temperature hot water to our campus to heat our campus buildings. So why would we undertake something like this that's so disruptive, so expensive, and is going to take us so long to do? We had two reasons. One is that our legacy steam infrastructure that was over 100 years old and has served our campus very well has been in failure for many years now, and we needed to do something. So the question really for us wasn't whether we were going to do something; it was what we should do in order to position our institution for the next 100 years from an energy standpoint. And then, like many institutions, we signed the American College and University President's Climate Commitment, ACUPCC for short, back in 2010. And with that, we pledged to be carbon neutral by 2035. And so you put those two things together, and that's what put us on our course that we're working through now. We did take some time in 2018 and 2019 to do a really in-depth study of how we might move away from our steam system or renew our steam system for the future. And I'd love to take some time to talk about each of these, but in the interest of time, I'm only going to talk about the pros and cons that we compared to in our financial analysis, which was renewing central steam infrastructure. And what that looked like was, okay, this is a known technology for us, and we know that we wouldn't have to do anything at the end of the line where our buildings are still receiving steam if we renewed the steam system. But it really didn't meet a lot of our other criteria if we were going to do that. We'd still have to put in new infrastructure. We wouldn't do anything for reducing or eliminating our carbon. And because of climate change, we really need to expand our air conditioning on campus into our residence halls that don't have it, just because it's getting hotter and hotter in May and September here, and our students are noticing it. And so we decided to look at a system that would also provide us opportunity to expand cooling throughout the campus. I do want to spend a little bit of time talking about this because people always say, Andy, what's the payback for this effort? And people are often asking, like, what's a simple payback and how many years until this pays for itself? But when we did our financial analysis, recognizing that we had to do something, our financial comparison for payback was, how does this compare with renewing the steam infrastructure, which we called our business as usual, or BAU for short. And this chart's a little bit out of date because we did it in 2018 or 2019, but the message is still the same. And what makes it out of date is we didn't really account in this for the high cost of construction inflation that happened as a result of COVID. And on the other side, we didn't account for the money we're getting back through the Inflation Reduction Act for this effort. or the high cost of building connections as we modeled them in the future. But the gist of the chart still stays the same. So pay attention to over the 30 years, looking at the red line and yellow lines, which are business as usual. What if we were to stay with the steam plant? And the red line is just the cost of continuing to renew and operate the steam plant over 30 years. And the yellow is, well, if we're meeting our climate commitment, what if we had the costs of carbon offsets to that for all the carbon we're producing? And if you compare that to the gray line, which is our trajectory, which is a phased installation of the geo-exchange system, you can see that somewhere between 18 and 25 years, those cross. And that's where we are spending the same amount with renewing the steam system. But then after that, we're saving significant money for the rest of the life of the system. And oh, by the way, we're eliminating our carbon, our scope 1 emissions in the process. And we anticipate that this new system is going to have a life between 75 and 100 years. So that's many, many, many decades of savings and carbon-free energy. So as we're going through this kind of recasting of our campus with carbon-free district energy, there are many elements that we set out to achieve. And if you just look at some of the bold, what we're achieving is resilient, highly efficient, and carbon-free campus heating and cooling. So I'm going to turn it over to Jill now, who's going to talk about what we're doing and how we're doing it. I'm still going to advance the slides, so you may hear Jill just give me a cue when she wants me to move on to the next thing.
Okay, sounds good. So I'm going to talk a little bit more in depth about the 6 components that Andy mentioned. The first one that I'm going to mention, and this is kind of a graphic of our campus overall, but if you can hit the enter, Andy, I'm going to kind of go through these quick. So the first is our geo-exchange plant, which is circled here in green, and you can see it's kind of in the center of campus. The next is the well fields that are in that light green, obviously adjacent, tried to make them close to the geo-exchange. Go ahead. And then the distribution system is shown here in the blue and orange lines, broken up into different areas of the campus. And I'm going to go into each one of these a little bit. And then the connected buildings, you can kind of see in gray, the connected buildings that we're trying to reach on our campus. Go ahead. And then because we're electrifying, making sure that we had consistent power, we did add on our South Campus there, standby generation plant, which does back up 100% of our campus. And then Andy talked a little bit about the renewable energy. We'll talk a little bit more about the VPPA at the end. Go ahead. So this is a macro view of the geo-exchange. It's obviously not to scale, but it kind of gives you a little bit of a feel for how the well fields interact. The same thing that we have here in the center of campus, the geo-exchange. You can see the piping going out to the buildings and the geo-exchange. Just a good overall quick view of our system. Go ahead. So here's the geo-exchange plant. It's a 3D model rendering of our geo-exchange plant. It is a centralized plant. We did one centralized plant for the campus. The plant operates in heating or cooling mode, but in either mode, we're still sending either the low temperature hot water and the chilled water out to the campus at any one time. It just operates a little bit differently. And then when we were looking at this, we looked at designing the plant to 100% future load, but we only built it out to 50%. And then we'll expand it as the load increases and we put more and more buildings on the system. And we really focused during the design on making sure there was reliability and redundancy done within the plant. Go ahead. So here's a little bit more information about the plant. Currently, we got 2 heat recovery chillers, expandable to 4. There's a series of pumps, water distribution pumps that bring the chilled and low temperature hot water out to the buildings. The geo-exchange pumps obviously go to the well field, and then heat exchangers. I think Brian mentioned a little bit about, heat exchangers. We do have heat exchangers in the plant, and then we've got tanks that help balance and provide room for expansion. The other thing, the electric infrastructure, making sure we increase the robustness of the electric infrastructure. Go ahead. Just a couple things to point out here. The low temperature hot water, we're making that leaving the plant or in the plant about 125 degrees. And then the chilled water, our target is 40 degrees. And then the liquid in the green pipes is really the temperature depends on whether we're in heating or cooling mode. Okay. Here is our heat recovery chillers. These are kind of a unique animal here. One of the nice things about these heat recovery chillers is if you see on top of the chiller there, there's actually 8 compressors, which allows us to, dynamically change the load, but also provides a little bit of redundancy. If one of the compressors goes down, we can isolate it and still have use of the equipment. So it provides a little bit of redundancy. Next slide, please. And then here's just some photos of equipment that's in the plant. I talked a little bit about the geo-exchange. So top left, those red pumps, and you can see the green piping that's going out to each one of the well fields. And then the heat exchangers are in the middle, kind of that black box that you see in the center. That's actually the heat exchangers. You can see the green pipe going in the one side, and then you can kind of see the blue pipe coming out the other side. So that's where we're exchanging that heat. And then just a picture of the buffer tanks, just some large tanks in there that help, give us a little bit of regulation as far as what we need. Go ahead, next slide. So moving on to the well fields, there was a lot of things that we looked at when we were designing the well field, which are listed here. Well field is kind of to the picture to the right. One of the things that I'm going to point out is the noise, because if you paid attention, the well fields are in the middle of our campus. So we have residential buildings that are to the right, some academic buildings that are surrounding the well field. So when we were drilling, noise was a real issue. So we really had to figure out how to do it and not impact or minimize the impact to the campus activity. So there's a lot of noise mitigation that was done during this and making sure that we only drilled during certain times. Next slide. So a little bit about the well fields. We do have 696 wells. They're 800 feet deep. Each well is 8 inches in diameter. There is U-tube going down. So it goes down 800 feet, comes back 800 feet, and then those are grouted in. They are set on 17-foot equilateral triangle grid pattern, which allowed us to kind of reduce the size as a typical square pattern that would be used. So using that triangular grid helped us with that. There are 6 zones, and in each zone there's multiple branches and consisting about 10 to 17 wells each. This is a closed loop system. You heard Brian talk about that a little bit. It's a closed system, and we do use in the well fields a glycol, 25% mixture of a non-toxic glycol is used. And it's, again, closed loop, so it never mixes with any of the water that we're sending out to the buildings. We did do the well fields at 100% future capacity because this was the, highly, I'm going to say disruptive of the campus, and we didn't want to have to go back and drill again. So next slide, please. This is just an overview of the zones 1 through 3 when we were during construction, and then the next picture. So this is after the construction is done and we've restored, and now these zones 1, 2, and 3 are in use, and you can see a little bit in the middle there to the left of the grass side, the vaults there that we can access the manifolds for each zone. And you can see, this is a good picture where you can see it's kind of in the middle of our campus. Next picture, please. So the distribution piping, so you need to get the low temperature hot water and the chilled water out to all the buildings. So we did look at that and designed it in a hub and spoke configuration. So we have basically, a line going out to each section of the campus, and then we branch off into each of the buildings from there. We did have an existing steam tunnel that went from our heat plant up to Parish Hall, which is shown in green there. We were able to use that north end of that tunnel to put distribution. I got a picture of it next to, but then we were able to use the south part to help get to the south part of campus. And then we direct buried PERT piping. We did have, instead of just HDPE piping, we did the raised temperature, just considering future. We don't ever want to have to dig up this distribution system again. And we are stubbing into the buildings, whether or not that we are converting them right away, we're still bringing them into the building so we're ready when we do the building conversions. Go ahead to the next slide. So these are just a couple photos. The one to the left is, a picture of our steam tunnel, and that's the chilled water piping on the left and the low temperature hot water on the right. A little bit bigger pipes than the steam, so took up a little bit more room. And then over to the right is the piping, the distribution piping that we're digging and putting in the ground. Direct buried, insulated, and this is just a good snapshot of what it looks like. So the standby generation was pretty critical for us. The grid here is not as reliable as we would like. And with going to electrification of the campus, and this is what we're needing to heat, it was very important that we had generation backup. So we did put in two 2.5 megawatt natural gas generators, which would only run on an emergency. And we do have plans to expand it to 7.5 megawatts. And this gives us some of the efficiency that we need. And then this is just a picture of what we did in the geo plant. The transformer is shown there to the right. The switch gear is a main tie main. So we do have a second transformer in an adjacent room. And this gives us a little bit of redundancy within the plant to be able to operate, make sure that we can get power to the plant. Go ahead, next slide. Building conversions, you can converting the buildings to low temperature hot water and making them energy efficient has probably been our most time consuming and longest part of it. If you can just, I'm going to fly through some of these because I'm not going to talk a lot, but we did have a huge mix of different types of buildings. They were all built at different times, had different uses, and a lot of different systems in it. So we spent a lot of time, go to the next slide, doing a lot of studies, did a lot of surveys, went through the buildings to see what was there and really account for it. Go ahead and go to the next slide. We did a lot of energy modeling and just different studies to figure out, what we needed to do in our buildings to convert them either from a steam system to the low temperature hot water equipment that needed to be replaced and what kind of energy efficiencies, that would affect. Go ahead. Also just try to model where we're going to put equipment. A lot of these buildings don't have a lot of room. So trying to figure out where we were going to put this equipment was another challenge. This is just kind of an overall concept of what we did in the buildings with heat exchangers and how it would work. I'm not going to go through a lot of these in details, but just to give you an idea of the in-depth amount of studying that we did with. And here's another example with the energy intensity. We also looked at the carbon emissions and how it would affect our carbon emissions. Go ahead to the next slide, please. And then we kind of broke down those into minimum, better, and best. Minimum, what do we minimally need to do, but what would be better and what would be best, including energy conservation measures to make sure that not only were we converting these buildings, but we were making them as energy efficient as possible. As Andy said, we're kind of designing these for long term. So ultimately, to get these building conversion scopes, it was 45 buildings that needed to be connected, but we took that information that we got from all the studies, figured out, trying to figure out what we're doing. We're still figuring out some of that, but we did convert the easy buildings first. So we connected about 10 buildings to the low temperature hot water, and there's about 26 buildings already connected to the chilled water. We also considered adding AC to it and what we needed to do with the domestic hot water systems. One thing that I'm going to point out here is we did put heat exchangers in each building, and that was, basically to try to improve the energy efficiency of the building, but it also allowed us to separate the building system from the campus system, and really make sure that we can operate the campus system and the buildings as reliably and efficiently as possible. Next slide, please. The building conversions was just probably our most time-consuming and complex part of the project. Costly part, was not something that we expected to be as costly, but we're trying to align some of that with major renovations. The last part of it is a virtual power purchase agreement, which was the last critical piece of the energy plan. And I'll turn it over to Andy to finish up.
Okay, thanks, Jill. So, one of the questions is, as I mentioned in that first slide infographic that we showed way back when, was how do we get enough renewable energy to power on our electrified campus? And in the Northeast, we don't have a lot of open ground near our campus. And we have a lot of trouble putting renewable energy onto our PJM electrical grid right now. And so there's a mechanism called a virtual power purchase agreement that allows entities to build new renewable energy and put it onto the grid and reap the benefits of the renewable energy credits from that, and therefore offsetting the carbon that we would generate from electricity that we're taking from the grid in order to power our campus. So it took us 5 years to get to a project. And we are a small institution, so we had to partner with 8 other schools to form a consortium. They're in Pennsylvania and North Carolina. And then through a consultant, partnered with NextEra Energy to develop a 900-acre site in Kentucky for solar. This is phase 2 of a portion they've already done. Nucor Steel was the first off-taker for phase 1. And this consortium is the off-taker for phase 2. So Swarthmore's portion of that is 20,000 megawatts a year, megawatt hours per year. And we expect this to come online in end of the calendar year 2026. And it's important to keep in mind here, we would love to build this next to our campus, but as I said, we don't have space, and carbon really doesn't care about borders anyway. And if we really start to dig into it, where this is, the grid is the MISO grid, which is an even dirtier grid than PJM where we're located. So by us offsetting some of that with renewable energy, we're probably accomplishing even a little bit more carbon-wise than we would be if it was local. So this has been a quick overview, and we're 5 years into or 6 years into a 15-year project, and we've learned some things as we've moved along. And I'm just going to hit a couple of the highlights. And the first one is cost. And so this isn't like building a building that we've built dozens of over the years and there's lots of data. This is a custom energy project with not a lot of experience out there. And so we made our best estimates, but we didn't account for COVID, construction inflation. And also it took us a few years after we committed to this to really understand what the full cost of converting our buildings was going to be, which Jill mentioned. And so we're taking that into consideration now, as well as many, many other external factors that influence the progress of a project over such a long duration, and that we have to be really flexible and imaginative in how we're responding to that and adjusting our path. And so where are we going next? A part of our assessment of these challenges over time is when we modeled the building connections and started thinking about the future cost, it was way higher than we had even anticipated. And so instead of saying, okay, we're going to connect all of our buildings by 2035, we're now moving ahead with what we're calling, or close to it, the accelerated steam plant decommissioning. So our single biggest source of emissions is our existing legacy steam plant, and we believe that we can shut that off by 2030 with this plan, eliminating the single largest, almost all of our scope 1 emissions for campus at that time, and eliminating a lot of costs because it's a very inefficient plant to operate. But that does require us to buy some carbon offsets for the small amount of carbon that we'll still be producing. So this graph and chart and table kind of illustrates how this might look. The steepest part of the graph is when we shut off the steam plant. And then depending on how quickly 2035, 2040, 2045, 2050, we connect the rest of the buildings, we've got a little bit of carbon from combustion that we still have that we'll need to offset, which is shown here in this chart. How many metric tons of that and at what cost that it would take us to do that over time. So that's where we're headed. Really exciting project. And I'd love to understand if you have any questions about it. So I'll stop sharing at this point and turn it back over to our moderator.
Okay, thank you, Jill, Andy, and Brian. We've got some questions. I have a couple, but I'll save them till the end after we do these. So I'll just go down. First one is, when used, does the aquifer get contaminated when the fluids are reinjected back into the aquifer? If not, how do you protect the aquifer? I guess that's for Brian.
Yeah, no, the fluids are treated before they are reinjected to remove any thing that shouldn't be in there. In fact,
Okay.
I know of one particular project in Northern California where they're actually using treated wastewater to refresh an aquifer that had been depleted. And it's been tested many times for everything under the sun and always comes back sparkling clean. So, yeah, that's not a concern, at least with modern practices.
Okay, and for the geologists in the crowd, is the high temperature in the western United States due at least in part to plate tectonic activity?
Yes, it is largely due to that. In fact, I don't know if you're familiar with the Ring of Fire term, which is a tectonic circle essentially around the Pacific Ocean. But that's all up and down the western United States, up and down the western side of South America, over New Zealand, and up through the eastern side of Asia. There is a lot of volcanic activity, and not coincidentally, that's also the prime spots for doing traditional geothermal, hydrothermal power plants.
Okay, this is probably more for our Swarthmore friends. Several other colleges are aiming to be carbon neutral. Can you comment on any of those? You're familiar with that at Mount Holyoke in Massachusetts?
Yes. As a matter of fact, I toured Mount Holyoke with my youngest daughter this summer, and I was musing about their project compared to ours. I know Smith College is working on a project. We've spent some time going to Princeton University. They're working in parallel with us. They're probably a little bit ahead of us, and their project is a lot bigger. Amherst is executing a project, Amherst College. I know Williams College is working on a strategy right now. Interestingly, they have a different geology, and I think when they were drilling their test wells, they realized they have to take a bit of a different approach than we're taking with ours, just because of the rock that we have that they don't. So there are several others. I'm sure that I'm forgetting many, but we all, the nice thing about working in higher ed is that we're not protecting trade secrets, and we collaborate regularly and share experiences with our peers.
Okay, next question is, was the Stanford SESI project looked at for ideas that uses above ground tanks for thermal storage?
Yeah, we talked with Stanford way back when we were planning. We're different climate, we're different geology, and so we did take some learning and information, but our system is a different system because we really need to respond to our own climate and geology for how we're working our geo-exchange.
Okay, are there special arrangements for areas that need to achieve humidity levels all year long?
Yeah, so I mean that's a challenge, but for the most part, the system. So we're sending out chilled water and low temperature hot water to the ones that are connected to the geo-exchange system. So we have the ability to control humidity through, normal means of you cool it down and then you heat it back up to you get the desired temperature and humidity that you want. So, we're looking at differential, um, you know, things in the temperature and that so we can do that.
Okay,
Hopefully that answers your question.
all right. Besides noise, are there any are what are besides noise, what are the real issues in installing the well field Swarthmore? What are the other issues, I should say?
Yeah, it's messy. It's messy, it's loud. Water mitigation is actually a big thing. The process of the well field drillers when they come out, there's a lot of site prep in order to make sure that we're complying with permits for NPDES and erosion and sediment control. And you also have to anticipate when we might interact with a ground aquifer and suddenly have a lot of water coming to the surface and how that gets handled, or because we're removing all the topsoil from the site before we even start drilling and stockpiling before we bring it back, the whole site is exposed to erosion. And you couldn't tell all that well from our images, but we're also working on a slope. And so in large water events, handling storm runoff and then the desedimentation of all of the water that comes up from drilling before it is then discharged into the stormwater system and ultimately the streams is really an important part of it. And then there's, just access around these large areas of campus where people are crisscrossing on a regular basis and how we keep that open, how we think about ADA paths and temporary paths when all this is going on. So this is not a simple endeavor, and there's a lot of work. Even more challenging is the distribution piping sometimes because we're going through a century of infrastructure on the campus and replacing old stuff and finding things that aren't documented that require ongoing engineering and redesign. And so it's tedious and it's slow. And we're going to really end up, when all is said and done, with a dynamite campus from a utility standpoint that we're going to pass off to those who come after us.
Okay, this is
Other
for
than
Brian.
those,
You may want to bring up your geothermal myth slides because they refer to specific numbers.
Yeah, I see that. And the myths in question are power plants take up too much land and it only works in certain places. To address the question, which is, that seems to be the majority opinion of professional energy managers in the Philadelphia area, and what to say to them, our executive director has a saying, which is that geothermal doesn't have a technology problem, it has an information problem. And I would say address it by just sharing some of the things that I said today, that new technologies have really geographically opened up opportunities elsewhere other than just the Western United States. Because they're not wrong. I mean, until fairly recently, at least power production was pretty much restricted to the western half of the United States, but that is changing very quickly. I would recommend, honestly, send them to our website, geothermal.org. We have a lot of information there, or send them to the Department of Energy's webpage on geothermal. There's a lot of great information there. And it really is a matter of just getting that information out because the technology is already there in a lot of cases and getting there in some of the others to really open things up geographically.
Or send them to Baltimore to your conference, right?
Absolutely.
Okay, so the last question would be, can a variant of this program be used to restore depleted aquifers?
Sorry.
Can a
Variant
variation of the
of,
program be
of
used to restore depleted aquifers?
oh, the one that I mentioned using the wastewater. Is that the
Yeah.
program in question? I'm guessing. That is exactly what it's being used for in this case. It's a very unique situation in the city of Santa Rosa and the geysers, where the geysers, I didn't really touch on this in my talk, but that was the first geothermal development in the United States. It was first developed in the late 50s. And they were not re-injecting it initially. So that aquifer did get depleted of fluids. And so it's been sort of an uphill battle getting it injected enough. And so they reached an agreement with the city of Santa Rosa and the surrounding area there to re-inject treated wastewater into there. So yes, I think it is being used for that way. However, it would take just the right set of circumstances probably to replicate it.
Okay, before we close, I do want to throw out one question out there for Brian, which is how much of the technology that's been used, in fracking and horizontal drilling spilled over to geothermal?
You mean from the oil and gas industry, you mean?
Yeah.
Yeah. There's definitely a lot of similarities there. And in fact, I would say that currently that's a big area of discussion is adapting some of the technology developments that the oil and gas industry has used. It is a little different in how it's done in geothermal. We are in both cases drilling into the ground to pull up hot fluids, but there are differences, but there is a lot of overlap there.
Okay, and there's one last question that came in before I turn it over to you guys to finish up. What do you anticipate is the major maintenance issue after full operation? I take that for Swarthmore.
Yeah, I can address that one. I mean, there's going to be various things. You're adding a lot of equipment, a lot of heat exchangers. Water quality is going to be huge, making sure that we're maintaining water quality, because if you don't, it will have the ability to break down a lot of the equipment between, the heat exchangers and the pumps. And a lot of controls. For this, it's a pretty complex system with controls and valves that operate. So making sure that we're staying on top of that and staying on top of just general routine maintenance as the equipment goes in. But again, I'm going to stress the water quality because that can make or break the system.
Okay, and do any of our panelists have final thoughts that you want to share before we turn it back over to Miranda?
I will just say that part of our one of our goals that I didn't articulate with this whole project is that this is exactly what we want to do, is continue to share that there's a path ahead with this for other institutions, and I think we're trying to demonstrate that, and we're always open to giving tours and sharing our experience with people that are curious about it.
Yep. Ditto. It can be done.
And I would just like to say that, while it was once very geographically limited, the new technologies are very much opening up things, possibilities throughout the country, and that geothermal is a clean, renewable, low emission resource with very small land footprint, comparatively speaking. So let's embrace it. And good luck to Andy and Jill with your project. That's really exciting.
All right, so I thank all three of our panelists. Thank you for staying with us, and I will turn it back to Miranda to close us out.
Thank you all for that wonderful presentation. Lots to think about. I just want to add that in addition to putting on free talks like today's, the very best part of the Science History Institute is that it's free, and your gifts power our programming. I would also like to remind everyone that the recording of today's presentation and past JPS talks are posted on our website. And please do come back for more. Let your colleagues and your peers know about our Joseph Priestley Society lectures and other compelling programs. We do have our next event is coming up in February, and it is in person at the Institute. It's on February 6th, and you can register through the link that's in the chat. And it's going to be on the chemistry behind wine, roses, and chocolate in time for Valentine's Day. So thank you all for joining us today, and have a good rest of the day.